This is part 2 of lecture 1.5 of Math 108, Predicates and Quantifiers. In this video, we will introduce the universal and existential quantifiers and their properties. As we said in part 1, a predicate is a sentence involving variables which does not have a truth value. Note that not every sentence which involves variables is a predicate, since it is possible for such a sentence to have a truth value. For instance, the statement x squared equals 1 is neither true nor false since we do not know what object x is. This sentence is a predicate. The statement x squared equals 1 for every real number x has a truth value since it makes a more specific assertion about the set of objects which make the equation true. We know that this is false since 0 is a real number which does not satisfy the equation. Likewise, the statement x squared equals 1 for some real number x has a truth value, which we know is true since 1 and -1 are real numbers which satisfy the equation. The phrases for every and for some, which we attach to the variable in the predicate, are called quantifiers. A predicate, together with quantifiers for each variable in the predicate, is a proposition. Let P of x be a predicate. Attaching the quantifier for every produces the proposition for every x, P of x. This is true if and only if the truth set of P is the entire universal set U. Attaching the quantifier for some produces the proposition for some x, P of x. This is true if and only if the truth set of P is non-empty. The quantifier for every is called the Universal Quantifier and is denoted by the upside-down letter A. The word every could be replaced by the words all, any, and each. The sentence for every x, P of x could also be stated as all x satisfy P of x, any x satisfies P of x, each x satisfies P of x, or every x satisfies P of x. The quantifier for some is called the Existential Quantifier. It is denoted by the inverted letter E. The sentence for some x, P of x could also be stated as there exists an x satisfying P of x. There is an x satisfying P of x. We can find an x satisfying P of x, or some x satisfies P of x. Note that the truth value of a quantified statement depends on the universal set U. For example, let P of x be the sentence x squared is a real number, and let Q of x be the sentence x squared is less than 0. When the universal set is the set of real numbers, the sentence for any x, P of x, which is the same as the square of any real number is a real number, is true. The sentence for some x, P of x, which is some real number has a real square, is true. The sentence for any x, Q of x, which is all real numbers have negative square, is false. The sentence for some x, Q of x, which is there exists a real number with negative square, is false. When the universal set is the set of complex numbers, the sentence for all x, P of x becomes false, and the sentence for some x, Q of x becomes true. So when evaluating the truth value of a quantified statement, we should always be conscious of the universal set being used. A predicate may involve more than one variable. In order for such a predicate to be turned into a proposition using quantifiers, we need a quantifier for each variable in the predicate. For instance, if P has variables x and y, then the following are propositions. For all x and for all y, P of x, y. This is an example of nested quantifiers since we can think of the sentence for all y, p of x, y, as a predicate in the single variable x. If we call this sentence q of x, then the original sentence is of the form for all x, q of x. We interpret in an analogous way the propositions for some x and for some y, p of x, y. For every x, there exists a y such that p of x, y. And there exists a y such that for all x, p of x, y. For example, consider the sentence, for any real number x, there is a real number y, such that x plus y equals 0. This involves two variables, x and y. The phrase for any real number x is stated first, so this applies to the statement, there is a real number y such that x plus y equals 0, which we view as a predicate in the variable y. This is the sentence written in symbols. The sentence, there is a real number x such that for all real numbers y, x plus y equals y, also involves variables x and y. The phrase, there is a real number x is stated first, so this applies to the statement, for all real numbers y, x plus y equals y, which we view as a predicate in the variable y. This is the sentence written in symbols. We will show later that in general, the order in which the quantifiers are written is not interchangeable. In particular, the sentence says, for every x there is a y such that p of x, y, and there is an x such that for all y, p of x, y, are not logically equivalent. However, two consecutive nested quantifiers can be interchanged if they are the same. Hence, the sentence, for all x and for all y, p of x, y, is equivalent to for all y and for all x, p of x, y. We can write this as for all x, y, p of x, y. Similarly, the sentence, there is an x and there is a y such that p of x, y, is equivalent to there is a y and there is an x such that p of x, y. We can write this as there exist x, y such that p of x, y. For example, consider the sentence, the sum and product of any two real numbers are both real numbers. Assume that the universal set is the set of all real numbers. To write this sentence in symbols, we need to introduce variables for the unspecified real numbers being referred to. Let us use x and y to denote these real numbers. The phrase, any two real numbers, involves the universal quantifier applied to each of x and y. We write this in symbols as for any x, y. The predicate specifies the condition satisfied by the numbers x and y, which is that both their sum and product are real numbers. This is equivalent to the conjunction of the statements x plus y is a real number and x times y is a real number. This is the sentence written in symbols. Next, we have the sentence, for any non-zero real number k, there are two non-zero real numbers which are not equal and whose absolute values are both equal to k. Assume in this example that the universal set is the set of all non-zero real numbers. The phrase, for any non-zero real number k, involves the universal quantifier applied to the variable k. In the phrase, there are two real numbers, we denote the unspecified real numbers using the variables x and y. This phrase involves the existential quantifier applied to each of x and y. We write this in symbols as there exists x, y. The predicate specifies the conditions satisfied by x and y, which are that they are not equal and their absolute values are both equal to k. This is equivalent to the conjunction of the three statements x is not equal to y, the absolute value of x is equal to k, and the absolute value of y is equal to k. This is the sentence written in symbols. You have come to the end of Part 2 of Lecture 1.5. Before you proceed to Part 3, you are strongly encouraged to do the exercises given at the end of these slides. Thank you for your attention.